Hello everyone! In this video we will continue to examine topic 7.3, the structure of matter, and in particular we will continue to unpack quarks, hadrons, and the strong interaction. Alright, in the previous video we introduced the class of particles known as quarks. Recall that there are 6 flavors of quarks: up, down, charm, strange, top, and bottom. They are all elementary particles, they are all fermions, and they interact via all 4 fundamental forces, or fundamental interactions. The list of quarks can be found here. They are organized into generation by increasing mass and energy. Now, quarks interact via what is known as the strong interaction. We've already seen the strong nuclear force before, and at that point in topic 7.2, we said, well, the strong interaction is secretly a force between quarks. And at that point, we were concerned with what is known as the residual strong force, which is sort of the leftover strong interaction that occurs between different nucleons, between protons and neutrons. And we will get to that. But fundamentally, the strong interaction is an interaction that governs, or is one of the ways in which quarks interact. Quarks interact in a number of different ways. The strong interaction is the dominant way they interact. The strong interaction is governed by a subset of quantum physics known as quantum chromodynamics. This is in contrast to the electromagnetic interaction, which is governed by quantum electrodynamics, QED. Quantum electrodynamics is the theory for which Richard Feynman is famous. Quantum chromodynamics came out of a whole bunch of scientists in sort of the 1940s, 50s, and 60s. And notice it is, its root is not electro, but in fact chromo. Chrome meaning related to color in this particular case. Why? Well, as it turns out, all the quarks have a particular color charge at a particular moment. Color charge is like an electric charge, except instead of positive and negative being our names for the different kinds of electric charge, as it turns out, there are 3 different types or species of color charge. We call them red, green, and blue. Notice red, green, and blue do not literally describe the color of the particular particles. They are used because red, green, and blue can be used in the way that sort of color can be used to describe sort of how the different charges interact. That was a little vague, so let me give you a more hardcore example, or specific example. When you have +1 positive charge and -1 or -1 negative charge, and you have those 2 particles in the same atom, we describe that atom as neutral. So that atom has sort of +1 and -1, and when you combine them the way that normal positive numbers and normal negative numbers do, there's a sense in which they sort of cancel out. The same thing goes on with color charge, except instead of 0, where +1 -1 equals 0, what neutral is white or colorless. And as you may well know, the way that color works, you can use red, green, and blue light, and if you shine them all 3 at the same time, you will actually see white light, or what is known in the strong interaction as a colorless light. The other way to get something that is colorless, as it turns out, is to use not red, green, and blue kinds of charge, but their anti-particle charge, or the anti-colors known as anti-red, anti-green, and anti-blue. Those are usually represented by using the colors that are exactly opposite red, green, and blue on the color wheel. So sometimes anti-red is known as cyan, sometimes anti-green is known as pink, and sometimes anti-blue is known as yellow. Now, quarks are found only in composite particles, so multiple particles known as hadrons, which we'll get to in the next slide. But the key ingredient here is that the composite particles that are permitted by the strong interaction are colorless. And for example, right, let's take a look at the proton, which is one of our most common or favorite quarks. In a given proton, a proton is always up, up, down, which we'll see in a moment. Why might that be the case? Well, consider the electric charge. We know that the proton is positively charged, +1. So if we're going to make it out of quarks and we're restricted to up and down, which are first generation quarks, then we know we have to pick 2 ups and 1 down in order to come up with +1 elementary charge. So the electric charge dictates that the proton has to be up, up, down. Now, of those particular quarks, the way color charge works is that each of those quarks will be assigned a color, although that color, unlike charge, can change over time. So as the particles undergo strong interactions, the color of any individual quark might change over time. But at any particular moment, one of the quarks in your composite proton will be red, one will be green, and one will be blue, giving a colorless or white hadron, which is that composite particle made of quarks. By contrast, an antiproton will have an anti-up, and anti-down composition. And the charge will be -1, and I'll leave that particular exercise up to the reader. Just remember that an anti-quark will have exactly opposite the charge of a quark. And then the color makeup, according to the strong force of strong interaction of the particular quarks within your antiproton will be anti-blue, anti-green, and anti-red. It is, this can seem a little strange, but things to remember: red, green, and blue do not actually correspond to the colors of the quarks. There is some underlying mathematics that we are glossing over because it is significantly beyond the bounds of this course that correspond to what we're calling color. Okay, this didn't come up from nowhere. But the pattern that we can recognize that is super useful and that we can see at this level is to say, okay, if there is this thing called color charge that is the property for which particles undergo the strong interaction, the same way that regular electric charge is the property by which regular particles undergo the electromagnetic interaction, then we can say we have a pattern here, which is that quarks come in these composite particles, and the composite particle must have a colorless structure. We will say a little bit more about that in the next video.